Welcome everyone. Thank you very much for joining us today. It's good to be back with this new webinar series. I am sure you have checked the full schedule already, but I will share a link to it anyway later on. Today with our CTO Roberto Bagnara, we will look back at the Toyota sudden unintended acceleration case and how that redefined product liability for embedded software. For those of you who are new to our webinars, I am Lavinia Battaglia, CSR at BUGSENG, and our speaker is Roberto Bagnara, who, long story short, is a CTO at BUGSENG, computer science professor at the University of Parma, member of the MISRA working group, and of the International Standardization Working Group of the C programming language. Only a last note before we start, questions can be written in the Q&A section throughout the entire webinar. Then at the end, we will take some time to reply. All right, then, let's turn this over to Roberto.
Okay, thank you very much. And let us start immediately. And let's have a look at the outline of my talk. I will start with up of the case. And I will go through the causes of what happened, and I will also talk about the consequences, so the impact this has had on the industry, and what has started changing and must keep changing, because we are still not there. First, an acknowledgement. This presentation owes a lot to several people and organizations. So Michael Barr and Philip Koopman were the expert witnesses in the Oklahoma trial I will tell you about in a moment. They wrote very interesting reports, which of course I used to build this presentation. Also, a very interesting report was provided by NASA Engineering and Safety Center, NESC, who investigated the reported Toyota unintended acceleration cases. I have used documents from the National Highway Traffic Safety Administration, NHTSA, which conducted several investigations on the cases, colleagues at BUGSENG, of course, and then I have taken material to various sources of the press. So thanks to all of these subjects for the material I borrowed. And also a very important premise. So this presentation should not be taken to detract from Toyota. Toyota is a great company, and the mistakes that were done in that project could have been done anywhere else. Okay? And also, I can say that some of the mistakes that were done in that project are done today in too many enterprises. I also should point out that Toyota invests a lot of resources in both the research and the application of software verification methodologies. So Toyota researchers are regular contributors to international venues where software verification technologies and methodologies are discussed. And concerning unintended acceleration, Toyota is pioneering a new acceleration suppression function, which has not to do with the problems we are talking in this presentation, but they have to do with the problem, which is confusion. So the driver confusion, especially at low speed between the pedals. So they are launching a new functionality which is set to be available starting from this summer. So let's start with a historical recap. So we start from this point. This is taken from the Associated Press. So in October 2013, an Oklahoma City jury found Toyota Motor Corporation liable for a 2007 crash where one person died and another was seriously injured. So the jury awarded 1.5 million United States dollars to each of the victims, and also decided that Toyota acted with reckless disregard. This is a technical expression in the legal terminology, And this in the US means that a second phase of to determine punitive damages is in order, and this was scheduled to take place very shortly after the first sentence. However, before that Friday, Toyota reached a settlement to avoid punitive damages. And shortly afterward, Toyota started an intensive settlement process to try to resolve around 300 personal injury cases. In reality, in the end, the number of such cases rose to around 400. So at the time, December 2013, Toyota had already spent $2 billion in legal costs. They had recalled more than 10 million vehicles worldwide. Its executives were subjected to congressional hearings at Capitol Hill, and fines were paid for violating the United States vehicle safety laws. So in March 2014, Toyota reached another 1.2 billion settlement with the Department of Justice in order to end the criminal investigation into the sudden unintended acceleration case. And the separate, even though it is the same amount of money which is used, it's another 1.2 billion settlement was the result of a class action promoted by drivers of Toyota cars who claimed that their cars lost value as a result of the unintended acceleration problems. Plus, more than 25 million had to be paid to Toyota shareholders that saw their stocks losing value due to the recalls. And so in the end, so to keep a long story short, the final bill of this story is enormous, really enormous. And not to talk about the extensive damage to public reputation. So this is just one of the examples of several accidents that were given a very wide and bad publicity for the car maker. So unintended acceleration, according to the definition by NHTSA, unintended acceleration is the occurrence of any degree of acceleration that the vehicle driver did not purposely cause to occur. This is, of course, not a problem of Toyota alone. There have been announcements, in some cases not confirmed, in other cases confirmed, about unintended acceleration issues caused by software bugs. And of course, unintended acceleration is only one of the manifestations of software faults that may put the safety of passengers and other people at risk. And the level of awareness of such issues has increased dramatically after the Toyota case, but, and this is my point, not enough, not enough. So the story is very long. I will skip through most of it because otherwise it will be an hour just to tell the story. So, however, the story starts in 2000, where a new electronic throttle control system is adopted by Toyota. It's called ETCS-I. The I stands for intelligence. Okay. And soon afterwards, starting from 2003, the National Highway Traffic Safety Administration starts conducting investigation regarding speed control problems. So any car owner can submit a report to the National Highway Traffic Safety Administration to notify this agency of the fact that something is wrong either with the vehicle or with the infrastructure. So there have been several such investigations, and basically all the investigations done by NHTSA were inconclusive. So they said no defects were found. However, they also repeatedly said that the NHTSA has not enough resources to investigate all the reported incidents. So we are talking about hundreds of compliance. Okay, so and here we are in 2005 to 2007, and some of these incidents have to do with floor mats. So some kinds of floor mats can interfere with the accelerator pedal, and the accelerator pedal may be trapped in the mat. So, and however, as we will see, only part of the incident could really be connected to the floor mats. There is the first case which is definitely linked to floor mats is 2007, and Toyota settles with the family of the victim for an undisclosed amount in 2007. But at that stage, an HTSA upgrades the investigation from preliminary evaluation, which is the first level, to engineering analysis, which means that an HTSA should conduct an in-depth investigation about the reported incidents. So in 2007, we have the first recalls of Toyota because of suspected floor mats that interfere with the accelerator pedal. Okay. There were many other investigations through the years. So as you can see in this slide, in total, there were 2,600 complaints that were reported, and some of them were rejected by an HTSA without even asking Toyota for the data. However, the story does not end here because these complaints keep coming. So in April 2009, NHTSA receives a petition to investigate throttle control problem unrelated to floor mat issues in the Lexus ES vehicles. And in August 2009, something happens that changes the public perception of the thing. So there was a fatal crash of a Lexus ES350 that was a car taken from rental in California that kills 4 people. And the occupants were on the phone with 911, and the phone call was recorded, and it was really something that was scary, okay? And what's worse is that the driver was a California Highway Patrol Vehicle Inspector with 20 years of experience. So a person who was very expert in how vehicles are made. He was in good health, and it could have quickly get rid of any floor mats interfering with the accelerator pedal. Anyway, NHTSA linked this incident to floor mats also in this case. In October and November 2009, the recall continued, and nearly 5 million vehicles were recalled in that period. So this is the family. Mark Saylor, the vehicle inspector, with his wife and daughter and brother-in-law, and this is what remained of the car that he couldn't stop. So it started to be very clear to many people that floor mats can only be blamed for some of the incidents. And in fact, in 2010, Toyota tells NHTSA that there may have an issue with so-called sticking accelerator pedals, and a further 3.4 million vehicles were recalled. And not only this, 1 month later, in February 2010, Toyota admits problem with brake software and recalls a further 400,000 vehicles worldwide. In the same month, February 2012, Toyota announces that a company called Exponent Consulting that Toyota hired had completed a report saying that the electronic throttle control system behaved as intended. So this report by Exponent was highly criticized by many because it was not neutral. There was a blatant conflict of interest in the fact that Toyota paid this company to produce the report, and the report was technically very, very weak. In February 2010, so the same month, the Wall Street Journal published an article saying that only one reader exists in the United States for Toyota black box event recorder. And this is located in Toyota headquarters in California. And moreover, Toyota said that this is still an experimental feature and can give false readings. So the hope to be able to properly investigate incidents using the black box were frustrated by these two things. Then in February, the congressional hearings started, and new evidence arose in March, revealing that both Toyota and NHTSA knew that there were glitches in the vehicle electronic system that could result into unintended acceleration. In March of 2010, under considerable public pressure, NASA was charged with the task of conducting an investigation on Toyota ETCS-I system, and the report was published in February 2011, even though it was ready much before. And in 2012, there were more congressional hearings, fines, and settlements. So to give you an idea of how distressing this might have been, this picture is probably significant. So Akio Toyoda, which was and is the president of Toyota, testifies at Capitol Hill. Okay, a new report by Exponent was published in 2012. This was received exactly as the first one, so conflict of interest and weak. 2013 is the judgment of Oklahoma City, and where the plaintiffs explicitly claimed that the unintended acceleration was caused by a malfunction of the ETCS-I system. And then the intensive settlement process, the settlement with the Department of Justice, and mass settlement. So this is the story. Now, let us look at the causes. So the Oklahoma trial said that more likely than not, the problem was in the engine control modules, which is embedded into this board. So the big black thing you see is a V850. It's the main processor, and there is a slave processor, which is an ESP-B2. So here is the basic architecture of the ETCS-I system. It takes inputs from the sensors that determine the position of the accelerator pedal. Another input is the mass airflow, and there are, of course, other vehicle sensors. And from this input, the ECM controls three things, but basically one thing. So the throttle control motor. Because the fuel injection and the ignition coil are basically a function of the throttle control motor. Okay, so this is the basic architecture of the system. What is not completely clear in this picture is that when the throttle valve is closed or almost closed, there is a depression on the side looking at the engine. And this depression is used for the power assist. And the consequence of this is that the ETCS-I system is safety critical. And in fact, pumping brakes with throttle valve fully open causes loss of brake power assist. And this means that the force required in order to brake the vehicle passes from something in the range from 7 to 20 kilograms to 80 kilograms. And as a result, braking, which is the most instinctive driver response, may not allow the driver to stop the car. And in fact, in several investigations, found that the brakes were completely burned by drivers trying desperately to stop the car. And drivers cannot be expected to take other countermeasures. So automotive is completely different from aviation, for example. In aviation, you have pilots that have been trained to deal with all sorts of emergencies, whereas car owners are ordinary people like you and me. So shifting to neutral is something that some driver might think about, but most will not. The driver might also think that shifting to neutral could harm the engine. So once upon a time, this was certainly the case. Or it might not know how to shift to neutral when the vehicle is in modes other than drive and reverse. Another potential action would be turning the vehicle off. The driver might not think about it, or it might correctly think that this would cause loss of power steering, which is clearly another very critical function of the vehicle, or might be afraid the steering wheel will be locked if the key is removed from the car. So the NASA investigation, as I said, was done under significant public pressure. So correspondingly, there was time pressure. The study started in mid-April 2010, and it only lasted for 4 months. So NASA was not given enough information, and in particular, they were given the software of the main CPU, so the V850, but the monitor chip also had software, and NASA did not receive the software for this. They were told that the RAM was protected with error detection and correction, but in fact the RAM is not protected this way. They were told that critical variables were mirrored in order to protect them from corruption, but this was not always done. And they were told that less than half of the available stack memory was used, but in fact stack overflow could occur. So NASA was unable to prove that the TCSI system was responsible for at least some cases of unintended acceleration, but did not exclude this possibility. And in the process, NASA found plenty of things that were highly questionable from a technical standpoint. So the expert witnesses of the Oklahoma trial, Michael Barr and Philip Koopman, had more time to conduct their investigation, and also they built upon the NASA report, and they were in fact more successful. So the two persons I already mentioned, so Michael Barr, he studied the TCSI software in depth and found the likely cause of the unintended acceleration. Philip Koopman studied the design documents and all the reports produced by NASA and by Michael Barr and others who had access to the code. So they found many serious problems, both with the system design and with the software. We'll briefly review them. And in their report, there is a lot of evidence that at that time, in that group, for that project, inadequate engineering practice was in use. So one might ask, why didn't testing the vehicle find the problem? And vehicle testing is, of course, of crucial importance, but it is impossible to test everything at the vehicle level. So there is a huge number of possible operating conditions. The failures may depend on precise timing sequences. There is a huge number of possibly intermittent faults and random memory corruption. So just to give you an idea, for the period between 2005 and 2010, Toyota reported around 35 million miles of vehicle-level testing and 11 million hours of model-level software testing. So if you divide this by the number of vehicles, this means roughly 1 to 2 hours per vehicle, and there is no way this can find all failures. And in fact, it must be admitted that the remaining testing will have to be conducted by end users. The fact that testing is not enough is well known. So this is a quote from Dijkstra, very famous, saying that program testing can be used to show the presence of bugs, but never to show their absence. And here another quote saying that basically testing of very reliable software is infeasible. So it will need a time that is clearly out of this world. So what is needed? Testing is not enough. What is needed is a rigorous process. So, and this is based, as you know, on the concept of safety integrity level. Today, it would be for the automotive sector ISO 26262. If for other industrial sectors, there are other functional safety standards. At the time of the ETCSI, the state-of-the-art were the MISRA development guidelines for vehicle-based software. So we have already mentioned those in a couple of webinars. These guidelines predate of more than 10 years, the beginning of the work on ISO 26262. And ETCSI is safety integrity level 3, not the highest level, but people still may die. So for those of you that are familiar with ISO 26262, this is what this would be nothing new. So the MISRA guidelines, of course, deeply influenced ISO 26262. So you should have a specification and design phase. You should select the languages and compiler. You need configuration management of products and processes, testing, verification and validation, and so on. So let us look at some of the findings of the investigations on the ETCSI software. So here we only talk about the main CPU software and not the software of the other CPU. So we are talking about around 3,000 source files, around 500,000 lines of code, decently commented. So you see that the ratio about the presence of comments is not bad. For the development of ETCSI, Toyota did not claim to have followed the MISRA guidelines. And in particular, they did not claim enforcement of the MISRA C guideline. If there was an auditable software process plan, NASA did not disclose it. So NASA was under non-disclosure agreements. Of course, they had to investigate, but there were things that they were not supposed to disclose. If there was a written safety argument, NASA did not disclose it. And Toyota and Exponent, on behalf of Toyota, claimed that there were enough fail-safes that would mitigate unintended acceleration. So, as you know, a fail-safe is a device that, in case of malfunction, intrinsically mitigates a problem. So, and fail-safes are absolutely necessary, so for several reasons. So let's start with hardware bit flips due to radiation. So depending on the kind of chip, you can expect 1 bit flip every 10,000 to 100,000 of hours. And optimistically, 2% of them are dangerous, so which means that you will have 0.2 dangerous bit flips or failures per million hours. If you assume that cars are driven 1 hour per day and only take into account the Camry vehicles built in 1 year, the result is that 1 dangerous fault every 12 days. Okay? So, moreover, there are software defects. They can corrupt memory, any memory, and they, of course, compound badly with hardware faults, which are usually not anticipated. And the moral is that hardware and software faults will happen all the time. So you need to have fail-safes. The fail-safes of ETCSI were shown to be defective and inadequate by investigation. In particular, there was defective fault containment, inadequate redundancy, and existence of single points of failure. For instance, there are 2 redundant copies of the accelerator position signals, but they both go to the monitor chip, the ESP-B2, for analog to digital conversion. So if the monitor chip fails, doesn't matter that you have 2 redundant copies of the accelerator position signals, you are lost. Let's talk about coding rule violations. So Toyota claimed to use an internal coding style with 50% overlap with MISRA C 1998, which was the version current at the time. And in reality, of the 127 rule of MISRA C first edition, only 11 were in the Toyota coding guideline. And as NASA found out, Toyota did not always follow its own coding rules. So this is something that happens way too often. It happens today. So companies having a coding standard and not following it. So in the case of that project, many switch statements, for example, were supposed to have a default clause, but in fact they did not have it. Of the 35 MISRA C 1998 rules that NASA tools could check, in 2010, this is still shocking. So the Eclair system dates back to 2010, and we were able to do much better than this. Anyway, in NASA, in 2010, they could only verify 35 such rules. 14 were violated for a total of 7,000 violations. And the team of Michael Barr found, with a more sensible tool, of course, 80,000 violations of MISRA C 2004. And the coding rule violations are known to be bug predictors. So this was observed by Les Atton, who published several papers on the subject, and by Toyota researchers as well. So here is a picture taken from a paper by researchers of Toyota, 2004, and showing by experimentation that for each 30 rule violations, you can expect 3 minor bugs and 1 major bug. So if you have many rule violations, you are likely to have few minor bugs and a few major bugs as well. Another of the findings of the NASA team was that the code contained 2,200 global variables declared with different types. So they were declared of one type in one module and with a different type in another module, 33 unsafe typecasts, 99 conditions that contained side effects, 22 variables that were definitely uninitialized, and 2 arrays of 16 bytes initialized with 17 bytes. And many of those are sources of undefined behavior, which will be one of the subjects for one of the next webinars, by the way, if you are interested. So spaghetti code. Spaghetti code comes in 2 varieties. The control flow variety is has to do with the control flow complexity. So even though there are today much better metrics to measure this, there is a relation between so McCabe complexity, cyclomatic complexity directly measures the complexity of the control flow graph, and indirectly it measures code testability and maintainability, changeability. So with a cyclomatic complexity more than 50, the function is basically untestable. And if the cyclomatic complexity goes beyond 75, fixing one bug in the function very likely will introduce another bug. So it's basically unmaintainable. And in the ETCSI code, 67 function had cyclomatic complexity over 50, And one of them, the throttle angle function, has cyclomatic complexity 146. The other variety of spaghetti code is the data flow flavor. And this is constituted by the use and abuse of global variables. So when you use global variables, you open the door to the possibility that changes in one portion of the code will affect other portion of the code. Okay, so interaction via globals is very difficult to reason about. So if you do this, you can only reason about the programs globally. So it's just like the goto. If you use gotos and don't use structured control flow structures, you will have to take into account who can jump here and where can I jump from here. And this means that, again, you will have to reason about the program globally. Okay, from the Toyota in this ETCS-I code, NASA found 10,000 global variables, of which 7,000 could have been declared static at block scope, and 1,000 could be declared static at file scope. By the way, there are MISRA guidelines that would enable you to know immediately about these 8,000 cases that you could reduce the scope. There were a lot of concurrency issues, so shared global variables also accessed by interrupt service routine were not declared volatile. Shared global variables were not always accessed with interrupt masked. Watchdog timers that were supposed to detect task death were operated by, were reset by hardware, so thus defeating their purpose. So the watchdog is such that the software must reset it within a given time. Otherwise, a trap will be raised and some remediation measure will be taken. If you reset the watchdog not by software, by hardware, the watchdog becomes useless. Error codes from the real-time operating system, such as task death, were ignored. And so the result was that Watchdog cannot detect the death of major tasks. Recursion also is a very important cause of these problems of the ETCS-I. So recursion is forbidden by all coding standards related to safety because it makes determining the worst case stack usage much more difficult, in some cases also impossible. So, and stack overflow is a very serious error. So in the ETCS-I code, recursion was used, and since they used a tool by Greenhills called GStack. GStack computes an approximation of the maximum possible stack size. However, in the documentation of GStack, it is written clearly that if you have recursion, the output of the tool is unreliable. And so, in fact, GStack said that the maximum possible stack size was 1,688 bytes, where in fact, they were allocating 4,000 bytes. So, stack space was, the stack was 94% full, even without any recursion. And moreover, there was no mitigation for stack overflow. In fact, the stack overflow could directly result into overwriting of a critical area in the real-time operating system. So, according to the Oklahoma City trial investigation, this is what more likely than not happened. So, recursion resulted into a stack overflow. The stack overflow overwrote a critical real-time operating system area. This overwriting resulted into the death of one task called task X which was very critical. In fact, it included the throttle angle computation and most fail-safe. The death of task X was not detected by the watchdog, that was reset by hardware, and as a result, wide open throttle and unintended acceleration. So let's come to the consequences. So why is the Toyota unintended acceleration case special? It's special because never before the software for some automotive equipment was so carefully scrutinized. So, and also not only scrutinized, but the findings of the scrutiny were so decisive in the trial. So the jury found that by not following the state of the art of the time in software engineering, Toyota was guilty of reckless disregard for the interest of others. So, and never before a jury has been lectured about things as random hardware faults, bugs in software, insufficient safety measure, sane embedded system programming principles, the MISRA Guidelines, the importance of coding rules, and the role of software metrics as bug predictors. And what has changed is also that now lawyers know where to look. You can find on YouTube videos where lawyers are teaching other lawyers how to find spaghetti in the code. This John Beasley is a former governor of Alabama, and is also the president of a very important law firm in the United States. So what has started changing? The attitude has started changing, but still it has not changed enough. So in order to let you understand what I mean, these are things that are still said way too often. Yes, we do the MISRA rules. The compiler has some warnings for them, ignoring the fact that compilers are very, very bad in checking MISRA rules. So we have explained this in a paper a couple of years ago. What? 3,000 violations? I don't care whether these are true or false positive, just silence them all. Okay, so silencing violations reported by static analysis tools without even looking at them. Come on, undefined behavior in C cannot be what you pretend it to be. And on the same vein, I don't care if C standard says it's undefined behavior, it works. So there still are very serious misunderstandings about the nature of the C language and the dangers that its improper use pose to everybody. Training, what training? Our engineers are very good. Or this part of the code has already been used in a former project. It is okay as it is. So these are provocative things that are true. I hear them said many times today, and these show that things still have to change. Another thing that has to change, that in part has changed, is the temptation of looking at the whole thing as a box-ticking exercise. Okay, I have a tool, I run the tool, and whatever the tool says, it's good. As an extreme example, this is taken directly from one of the exponent reports about ETCS-I. There is a table produced by a tool, and then the exponent report says, table 10 shows the following, that 96.26% of the code in the analyzed models does not contain any runtime errors at the language level. And table 10 says nothing like this, absolutely nothing like this. So the policies have changed, and they still have to change to a certain extent. And the attitude should become that a non-verifiable piece of software is a broken piece of software, that a verification tool that hides what it cannot prove is a broken tool, and it doesn't help bragging tool certificates saying, oh, I'm using a certified tool, and completely ignoring the fact that you may have misconfigured the tool, completely forgetting about what the certificate is actually saying. And properly trained personnel is key. And these issues are becoming explosive right now because of several factors. You will know about this. Autonomous driving, connected cars, Internet of Things, all this compound to the fact that these issues are going to be more and more important in the future. So, to conclude, the October 2013 Oklahoma City trial marked a turning point in the definition of product liability. So basically, a jury said, we will investigate the software. We will have an expert witness judge whether the software is adequate, whether it was developed following the currently recognized state of the art, okay, which today would mean ISO 26262, MISRA, and so on. Never before has the source of embedded software been scrutinized so carefully, okay? And things will never be the same as before. And as I said, if not for other reason, because lawyers now know what to do and how to do it. And the embedded software industry should increase the efforts in improvement of software and system processes. So we should stick to the true state of the art in process, design, development, and tools. And look, I'm not talking about a box-ticking exercise. I'm talking about the real thing, not just the pro forma minimal requirements of adoption of some best practices, only some of them may be out of their natural context. Okay, so the presentation, I'm done with the presentation. If you have questions, I will be happy to try to answer them.
Okay, Roberto, thank you. So we've got a couple of questions. Let's go with the first one. Suppose we are adhering to ISO 26262 2011 for a project that started after 2018 version was released. Would there be legal issues if any recall happens due to unsafe scenarios?
So I think that so the meaning is, since the project started after 2018, ideally it should have been based onto the 2018 version of ISO 26262, right?
I think so, yeah.
Yeah. So I think I am not qualified to answer this question from a legal standpoint, but I think that if the project started after 2018 and was based on probably it's the initial conception of the project started before 2018. So I guess it may be okay. So, but this really, I'm really not qualified to offer legal advice. So in the end, if something goes bad, you will have to, in the worst possible case, you will have to convince a judge or a jury that you followed the state of the art that was current at the time when you developed your project.
Okay, thank you, Roberto. In the Toyota case, a good deal of bad luck was involved, wasn't it?
Yes, a good deal of bad luck. So very bad things happened, in particular from the chain of events that led, according to the investigation, to the you had recursion. Recursion resulted in stack overflow. The stack was adjacent to a critical real-time operating system area, and this resulted into the death of a task that the Watchdog did not offer protection about this. So yes, this is really bad luck, but you must also consider this. Okay, you may think that the chance of something similar happening again are a little, because it is a concatenation of events that is quite peculiar. But if you multiply the chances with the damage has been enormous. So we are talking about the death probably of hundreds of people, and damages to Toyota that are really enormous, as I said.
Okay, does ISO 26262 include MISRA C adherence within it, or we should consider compliance to MISRA C separately?
Okay, ISO 26262, as the majority of functional safety standard, prescribes the use of a safe subset of a programming language. So ISO 26262 does not include the word MISRA in it. It says that you should use language subsetting in order to exclude features of the programming language you have chosen that are dangerous or that can easily result into unwanted behaviors. So if you comply with ISO 26262, you will have to choose a programming language. You may not even choose C or C++, in which case MISRA would not apply. But if you choose C or C++, I strongly believe that today the state of the art in language subsetting for C and C++ is MISRA. So yeah, so ISO 26262 plus C or C++ in practical terms today implies MISRA.
Okay, it seems that the core IDE experience has been known more than 40 years or more based on my experience. Tools are much more excellent now, but even now, the problem could be on human side. People may not know we should use new tools and our experience together. Do you think it was and not experience together? What do you think?
So let me.
It's a long one. Sorry.
So it's a very long question.
You can find it in a Q&A section if you want to get.
Okay, so let me try to read it myself. IDE means integrated development environment. I don't know. Could be on the human side. Should use new tools and past experience together. I'm not sure I interpret correctly the question. Anyway, it is clear that what is called for in order to avoid this kind of problems is the use of tool coupled to the use of human judgment. So in particular, as I said, training is key. Okay, the use of static analysis tools is, of course, nowadays unavoidable, but also peer reviews are crucial. So peer reviews and so human judgment are essential as the use of static analysis tools. So, for example, so let's make a simple example. We have been talking about global variables. Okay, so global variables are bad in general. Doesn't mean that you should not use any global variables. The MISRA guidelines tell you when you are using a global variable unnecessarily. So this will be flagged automatically by the code. For the remaining global variables, peer review would be necessary. So the tool can hardly be have the required information to know whether this global variable is actually required or not. To make an example, so some variables must be global because you need to access them using a debugger or using an external probe. Okay, so this is something that the tool cannot know unless provided with a proper program annotation.
Okay, next question. Is there any coding standard available for Python which could use in TCL tool? And the same person asked, is there any static analysis tool available for Python code?
Okay, Python is really outside my field of competence. I guess there are some static analysis tool for Python. So until, I don't know, 5 years ago, I think there were none, but something was proposed. So I've seen it in some research papers that some of the obstacles at providing a precise enough static analysis for Python was resolved. However, I really am not competent to answer this question without preparation.
You mentioned about the error detection and correction. Is this hardware or software safety mechanism?
Okay, in the case of the Toyota investigation, the information was provided that the static RAM had hardware error detection and correction mechanisms. Okay, so this usually work by storing extra bits. So in the simplest case, which is not very effective, you would use, for example, a parity bit. So you would be able to detect some errors and not to correct errors. So using more bits, you can, at the hardware level, detect and correct some errors. So in the setting of this talk, I was referring to hardware error detection and correction devices for RAM.
How can the automotive companies detect if the driver has operated his vehicle incorrectly, causing accidents? Is this included in the ISO 26262 scope?
So I don't think it is, but I'm not familiar with the entire ISO 26262, so I'm familiar with the part having to do with software development and tool qualification. Anyway, the facility that was already present, what I call a black box in cars, is something that is more and more common today. So, for example, I mentioned some reports against Tesla models about unintended acceleration, and they, of course, I call it black box to simplify things. So Tesla models have a black box, and the investigations performed by Tesla in those cases, I think they were reported in 2016 and 17. Tesla concluded that the acceleration was caused by the driver. And so, in fact, it was not unintended acceleration.
In Toyota case mentioned, WDT is serviced during hardware GP timer, so it should use software timer to service the WDT.
WDT, I guess, is what is it? It's a Watchdog timer, I think. So whereas GP timer, I don't know what it is. So I can try to explain what I said, maybe in a confusing way. So a Watchdog timer is something that ensures that a certain piece of software reaches the end of the intended computation within a certain deadline. Okay, The deadline is verified by hardware. So unless the software resets the watchdog expires, and from hardware, something like an interrupt will be generated. So the mistake in the ETCS-I design was that resetting the timer was done in hardware as well. So this is why the watchdog timer was in fact ineffective.
Okay, let me check if we, oh, there is a new one. Well, a lot of questions today. What are the safety standards used for ADAS and AV autonomous vehicles domains? Is it ISO 26262 itself?
It's ISO 26262 plus other standards which in part are being developed right now. So it's actually an open an open field. This so things are happening quite rapidly, and further standards are under development that will hopefully be mature enough before we will find autonomous vehicles in the roads with us.
Okay, we're running out of time. So, of course, if you have more questions, you can always drop us an email at info@bugseng.com if you don't mind. Thank you, Roberto, and thank you, everybody, for joining us today. If you'd like to see this webinar again, of course, I shared the link in the Q&A section before. We will upload it very soon on our YouTube channel, and in general there you will find many interesting videos from previous webinars as well. Hold on just a second and let me remind you that next webinar will be MISRA Compliance 2020 for project managers on June 23rd, which is Tuesday next week. We know that project managers have a huge number of decisions to make every single day. So with that in mind, we decided to introduce a couple of webinars specifically for them. So if you're not a PM, please spread the word to your project managers. All right, that was all from me. Thanks again, and I hope to see you all very soon. Bye-bye.
Bye-bye.